Okay, looking at the quiz here. Question number 1. How many elements compose 98% of the Earth's crust? 6 or 8? 8, okay. So that limited it to these two. And then we have to have which one makes up 33% of the Earth's mass.
Iron.
Okay, the correct answer is iron. Now here is something to think about. Which has more atoms, oxygen or iron?
Iron.
If you look at the masses, oxygen has 16 atomic mass units. Iron has what, 50? I can't see here, 28.
26.
No, I'm in the wrong place.
26.
It's 56. So iron's 56. That means iron is more than 3 times the mass per atom. So that means if we take the masses, oxygen is just under 30% of the mass of the Earth. If we take the iron number and divide it by 3, that would tell us about the number of atoms. So there's actually a lot more oxygen atoms in the Earth than there are iron atoms. But the person who wrote this question asked about mass because that's what was in the graph we had, the pie chart. So it was the correct answer, but you have to make sure you're aware of what you're measuring. You're measuring the mass, not the number of atoms. The mass is probably the one that's more useful to you, right? You don't drink a cup of milk and talk about how many atoms you drank. You could talk about the volume or the mass. Okay, number 2. Which of the following is not one of the elements that make up 98%? I took out the word 8 there. If I had, then it would have, given you a clue to the other one. So which one is not in that list? Helium. Helium is a noble gas, and it's a gas the Earth can't hold on to. If Earth can't hold on to it, how is it that we even have helium? Well, we lose it in the atmosphere. But since we're losing the atmosphere, how do we still have helium? We make it. Now, we don't, you and I don't. Radioactive rocks like uranium produce helium because when they decay, they eject an alpha particle, which is a helium nucleus. And that helium nucleus, as soon as it grabs a couple electrons, it just becomes a happy helium. And so the way we have helium today is because of it being constantly produced. So these other ones, iron, number 1, oxygen, number 2, silicon, number 3, and then I don't remember what the rankings were after the big 3. But those were, so calcium was also one of the big 8, the most common. Okay, which is not one of the fundamental types of rock? Magma. What is magma?
Lava underground.
Oh, you know what? I didn't have that question. I told you it was on here, and it's not. Well, it's in the database for the test, that's for sure. Okay, magma, some people said lava. What's the difference in magma and lava? Because that was the question that Vanessa gave.
Magma is still underground.
Okay, magma is molten rock underground. Lava is molten rock that's reached the surface now. So we don't have magma flows on the surface. We have lava flows on the surface. But underneath, we have magma. And finally, which of these is not an example of an igneous rock? Okay, Casey doesn't know, but she answered correctly.
Answer is shale.
Yes.
That's such a great.
You have a question, Jocelyn? No. Just a celebration?
Yeah, no, not a celebration.
Oh, the other kind. The what the heck? Sorry about that. Shale is what's produced when you have a very fine-grained sediment, like mud. No, it's called sandstone if it's sand, if it's a thick grain. And there is a grade that's called mudstone, but shale is very fine-grade sediment. So like you have silt, and it gets compressed, and it forms that shale. So when you hear something about fossils in shale, well, those fossils are there because you had this fine grained sediment that came down and buried poor little fishies or whatever else was there. And that's how they became fossils. They got buried in material that then would become rock through the sedimentation process. Okay, let's stay on this page, on the quiz page. Actually, no, let's go to the one for today's lecture. And Brittany Renee Simmons wanted to ask a question about homework.
Number 37, which is also number 3.
Okay. Both of those mean nothing to me. Can you tell me what the question is about?
Oh, it says, okay, so referring to figure sites, by the way, it's not page 000.
Excellent.
It does not exist. It took me forever to find it.
Did I have a mistake somewhere?
Well, in the book.
In the book it says, go to page 000.
Oh, I see.
And so, like,
Okay.
I was like, I don't know where that
Is
is.
this the one about the mass percentage?
Yeah, so what are the mass percentages of the oxides, magnesium oxide, iron oxide, and silicon
Okay.
dioxide?
Okay, the one where I gave you a little hint. I said, yeah.
The book.
I added in the form of to the hint that they gave you. So there was in the book, it said refer to a page that was wrong.
Refer figuring science, silicon enrichment, and magma on page 000 to solve the following problem.
Okay. Yeah. I only looked online and I did not see that reference. Okay, so we have Mg
Right. I'm like,
Fe Si2O6, right? And so it gives us a hint.
there's commas in between all of each of those.
No, this is not the first reading, but the place where it gives us the compound.
That's the pyroxene.
That's pyroxene, yeah.
Okay.
Okay, so this is what we have, and we're told to put it in the form of, and I gave this MgO with some subscript, and then FeO with another subscript, and finally SiO2 with some subscript. So if we look at these, I say, in that base formula, how many magnesiums do I have? 1. So that means I better have a 1 here, because there's 1 magnesium. Now I'm going to count my O's. So I have 1 O from that one. Now we go to the iron. How many irons are in my pyroxene? So I'm going to have 1 there as well. So I'm going to have +1. Did you have a question, Brandon? Okay. Just wanted to make sure I'm not ignoring an important thing. Then we finally get to the silicon. How many silicons are in there? 2. So I better put a 2 down here. And so that's going to be plus. I have 2 times 2, 4. And so that gives me a total of 6. So now I've gone through my magnesium, iron, and silicon. Now I just have to check and make sure my oxygen's right. If my oxygen's right, I'm good to go. So there's 6 up there, and I have 6 here. It's good to go. So this is the form that the hint tells us to write it in. Now, it's not the answer, but it's what's going to help us solve the problem. So now we have how many kilograms of silica are in 225 kilograms of pyroxene? Oh, goodness. We have to do some math. I know. We're just going to take each one of these and do the maths. So magnesium, iron, silicon, and oxygen. So Brandon, you're the closest back there. Just give us, round it off to the nearest whole number, the number in the bottom of each box. So for magnesium, what's the number in the bottom?
24.
24? So that means it has roughly 24 atomic mass units per atom. Okay, for iron.
56.
For silicon?
28.
28. So if we take these, we can then combine them to say MgFeSi2O6 is equal to, well, actually, let's not even worry about that. We'll do that at the end. Let's just do the minerals they gave us. MgO, magnesium oxide, which I studied a lot for my doctorate. Magnesium oxide is just going to be a mass of 24 plus 16 is 40, right? And then if we do FeO, that's going to be 56 plus 16 equals 72. And if we do SiO2, that's going to be 28 plus 2 times 16. Why 2 times 16? 2 oxygens, right. So that's 60.
Why is it not twice?
Why is what?
Why is it not twice?
Well, I'm just calculating the mass of SiO2. So these are
There's two of them, right?
there are 2 of them in this, yes. So now if I calculate the mass of that thing, the mass of the whole is equal to 40 plus 72 plus 2 times 60. There's where the 2 is you were looking for. And so that's, if we add them up, $232. So these are all in atomic mass units. Now I'm able to do the problem because I know what percentage of each one is going to be. So part A asks us how much mass I'm going to have of silica if I have 225. I've run out of space. Next page. So I have part A, 225 kilograms of pyroxene. How much silica? Well, all I have to do is take the numbers we've just done. That's going to be 225 kilograms and multiply it by the mass of silica, which was 60 atomic mass units, divided by the mass of the entire thing, which was 232 atomic mass units. Right, so I just took the ratio of the mass of the silicon dioxide to the mass of the entire thing, and I multiply it by the entire mass. So if its mass was 1/3 silica, I would have had 1/3 times 225. And so now you just have to put that in your calculator. I'm not going to put it in a calculator. After all, it is your homework.
How did you get to 25?
That was given in the problem, right?
Oh.
And then part B asks us if 325 kilograms of olivine and 225 kilograms of pyroxene have crystallized out of 1,000 kilograms of magma, what is the mass percentage of silica in the remaining liquid? Olivine, we didn't do any calculations for. And it's not written here, and I don't know the chemical formula for olivine.
I know that olivine crystallizes before pyroxene.
What was that?
I don't know.
So for the olivine, for the part B, we'll have to go through and we'll have to calculate how much silica by percentage is in olivine. And then we can calculate how much silicon has crystallized out of the 1,000 kilograms.
You're supposed to know how to do that?
What was that?
Where did we get that from?
Yeah, I don't, well, I'm sure the textbook has the chemical formula for olivine. Yeah?
For that equation, shouldn't it be 120 something?
Did I do it wrong?
Yeah, because it was.
Oh, you're right. Because there are two. Yes, you're right. It should have been 2 times 60 because there are 2 silica per, not 1 silica per. Thank you very much, Stacy.
I told you.
Okay, so let's just, to make it easy, let's go ahead and skip part B. That is, don't do it on your homework. I won't grade part B. Just because I don't know what olivine is offhand.
It's what
And-
they give in the book or something.
Yeah, shh, shh, shh. They don't want to do it. And well, there's one other problem here because we actually don't know what the percentage of silica was in the original fluid. It doesn't, at least I don't see in the problem where it says what the percentage of silica was in the initial fluid. Right, because if it was basaltic, it would have been 50%. If it was granitic, it would have been 70%.
It says it's
It's where's it say that?
no, it's in the page that's the reference.
Oh.
In the box. It gives you the.
Oh, it gives you that information there. Does yours actually tell you the page, or did you find it?
No, I found it and I said it's given on this.
Yeah. Okay, now we're already 40% through the lecture, so that's all the homework I'm going to do because of the time we've already used. We're going to finish up chapter 20 quickly and then get into 21. So I've already talked about evaporites. We've already had people turn in questions on evaporites, so I'm not sure why I left that one in there. The process of making coal is an interesting process. It's an important one for us because, well, we do use coal. And in fact, I believe yesterday, our president made a promise that we're going to bring back the coal production in this country. Which, you know, to a lot of people is a less than favorable promise because there's a lot of pollution involved with burning coal. But here's how coal is made. You first have a bog that's growing a bunch of biological material. So here's your swamp growing that biological material. That biological material then gets buried and it creates what we call lignite. So it's the peat is biological material that's here in the bottom part of the swamp. One of the things that was really cool when I was in college, we went on a choir tour to England. Just cool. And they had a body that had been found in a peat bog in a swampy area that had peat down there. One of the things that goes on is you have all this biological material that uses oxygen, it depletes it of oxygen. And because that area down here is depleted of oxygen, things don't decay. And so he was very, very well preserved after thousands of years because he had been buried in this anaerobic environment. So then compaction causes it to pressurize and it makes it change. You get to the bituminous. You might have heard of people talking about coal as bituminous. And so this here then can be dug up, the anthracite, the final form, dug up as a rock and burned very hot. So it's a natural cycle to make the bituminous or anthracite coal. It's natural. Why would I be against coal like I just said a few moments ago if it's natural? Not everything's natural is good. Right, Raquel?
Can you go over 2, 3, and 4 again, what they are?
Okay, lignite is a compacted biological material. So you have plants, right? Carbon-based life forms, if you will. And then it's been compacted. And that's how it forms the lignite.
So the first one is biological material and that one's just compacted?
Yeah, the peat is basically you have growing plants and it's buried in an anaerobic environment. So when we burn fossil fuels, like this is a fossil fuel because it's plants. We burn the fossil fuel of plants here in coal. We release a lot of contaminants into the environment. Is this considered a renewable energy source?
No.
No is the correct answer. Right now, we don't have any knowledge about new coal being formed in West Virginia, right? Because they don't have the situation there, the swampy situation. It's necessary to start it. And then it takes very long amounts of time for the compaction process to convert that peat bog into coal. So it's a very long time scale. Because of that long time scale, we don't consider it renewable. Once we use up what's buried in the ground, we have to wait a few million years before it's replenished. Now, oil, the process of oil production is identical to this except for the first stage and the names. The first stage for oil production is you have animals living on the surface of the earth. And then those animals die and get squashed. And over time, you have decay, and what's left is oil. But once again, it takes a very, very long time. So, the oil fields are places where you had a lot of animals that got crushed and compacted. And, how long does it take? Has anybody ever gone out and looked through shale for fish fossils? No. Well, you'll find some shale that they call oil shale. Oil shale. And that oil shale, it totally smells like oil. And you can throw a match on it and it will burn. Why? Because the little fishies got squished and converted into oil that's in that rock. Or if you go up to Canada, you guys know about things like the Keystone Pipeline, right? Keystone XL Pipeline, which you totally should be aware of because they want to put the pipeline under the Ogallala Aquifer. And as much as they say there'll never be a problem, it seems like every month or two we have a pipeline that leaks somewhere causing contamination. We don't want to contaminate this huge aquifer. Sorry, political statement. Where does that oil come from they want to put through the Keystone Pipeline? It comes from oil sands up in Canada. In Canada, they have sandstone that is permeated with oil. And so they dig out the sand, they heat it up so that they can separate the oil from the sand, and then they use the oil. So that's a naturally produced product, but we don't consider it renewable because it takes so long. Raquel.
So do bones ever decay?
Do bones decay? Bones are essentially rock, calcite rock. So they really don't. So when you actually look at old, at fossils, I was going to say old fossils, but what's the point of putting the word old in front of fossil? When you look at fossils, what you have there is basically bone.
Yeah. I was just wondering maybe it was a little longer.
Okay, moving on. Metamorphic rocks. We already had one potential test question on metamorphic rock. So now we'll actually cover them. So metamorphic rocks are rocks that have been converted by pressure and temperature, as well as chemical access. I know you have a homework problem that says 2. Temperature, pressure, and chemical are 3 things that will contribute to metamorphism. So metamorphic rocks start out as one of the other 2, as igneous rocks or sedimentary rocks. Sedimentary rocks, obviously the lazy ones that sit on sofas. Igneous rocks producing fire. Either one of those can be metamorphized. That is, you put them in a condition where it gets hot and they partially melt. They kind of squish like you squeeze a tube of toothpaste and it comes out squishy. And then it, of course, cools down and hardens up again, giving you a deformed looking rock. What's the most common metamorphic rock that you are used to seeing?
Obsidian.
No?
Basalt.
No.
The other one.
It's marble.
Marble. That's what I was
Marble, you know how marble has the nice little whorls in it and whatnot? That's because it's been metamorphized. It's been squished, causing things to swirl around like that. So marble is an example of metamorphic rock. Not the only example. So how does that occur typically? Do you remember what we call a pocket of molten rock?
Pluton.
Yeah, it says it down here. We have a pluton,
Well, I didn't
or a
say
batholith. Yeah, I trust you. Well, that's going to heat the rock around it. But of course, it can't melt everything. And so you have the rock that's just in the border around it is partially melted. You get water in there, and the water will help the process. And you'll have, as you see here, stuff will be deformed, squished, heated up, and then later refreeze. And that's how you get metamorphism. Yeah, move past there. Metamorphic rock, you have it broken into foliated or non-foliated. A portfolio, same basic word. You have sheets in your portfolio. Foliated is sheets of material. So if we look at, the only one that's coming to mind is, well, I'm not going to say it because you'll think I'm saying a bad word. The only one that came to my mind was this one here. And yes.
Just how to pronounce the S, dude.
We have funny jokes in geology. Things like,
That one's nice.
she thought the rock was nice, but I took it for granted. Right? Because nice is this kind of rock. And of course, the true phrase should have said granted, but granite is another type of rock. Yeah, you can see how humorous geologists are. Brittany's well on her way to join the geology community now, I'm sure. There is another part to it that uses rock B, but of course I don't even know what that part is because I never say it.
I just said
What is that pronounced? What is that?
Which one?
The last one?
Nice. Right, so that one actually is pronounced correctly in that little joke. Okay, so this is slate. What is slate good for? Chalkboards. It's good for chalkboards because it is a foliated metamorphic rock. The foliated has sheets, so you can make it nice and flat pretty easily because you just split it on one of those sheets, just cleaving it, and you can make it nice and flat. It's also used, by the way, for shingles, slate shingles. Obviously, they're fireproof shingles, which is good. So these are examples. Notice here in the gneiss, you see the clear deformation that it's undergone. Right? Nobody's going to look at that and say, yeah, that looks like it formed in a lake bed with nice horizontal layers of rock. Right? Because that's not what it looks like at all. Non-foliated marble and quartzite are non-foliated. That is the marble. You can't just cleave the marble. You have to polish it to get your shape you want. And, well, quartzite is this thing here. The last thing on rocks. What is the rock cycle? The rock cycle is the cycle of rock recycling. Rocks have the three types, but ultimately it's a big recycling process. Because you, for instance, melt rock. It doesn't matter if it was a sedimentary rock or a metamorphic rock or an igneous rock. You melt it and now it's magma. And whatever freezes is then going to be which kind of rock? It's going to be igneous when you freeze it, no matter what it started out as. So you melt the rock, it freezes, and you form an igneous rock. Well, then that igneous rock undergoes, and let's refine these terms. And by refine, I mean you just tell me what each one means. First, it undergoes weathering. What does that mean? Okay, stepping on it is an example of what causes weathering, breaking the rock apart. So you break little pieces off. I didn't hear what you said, Jackie, so I just couldn't go with it.
It was good.
Were you correct?
Yeah.
Excellent, Jackie. Okay, after weathering, then you have erosion, which is?
the wind. No.
Wind is an option for erosion. Wind and water are the two primary vectors for erosion.
Transporting rock.
Transporting of that broken up rock. Then you have the
Deposition.
settling, the deposition, and finally the sedimentation, it being lithified, cemented into a rock.
True.
So you make a sedimentary rock. That sedimentary rock then could undergo weathering again to make more sedimentary rock. It could be heated and metamorphized, or it could be heated and melted again. So the material just keeps going around in cycles. So that's the rock cycle. Now to chapter 21. Chapter 21, plate tectonics. Let me jump forward to a picture to start this thing all off. Jump way forward. Way forward. Okay. Has anyone ever noticed by looking at a world map that it looks like you could take South America and Africa and they would fit right together?
Yes. Yes.
Yeah. Good.
Pangea.
I noticed that when I was a kid and I thought, wow, that's weird. I wonder if they were together. Well, Wegener, I think it was around 1920-ish, he noticed that and he said, I think that we used to have a single continent called Pangea, and that somewhere along the way, this continent broke apart and has been sliding around, so that our Earth has pieces sliding around. And of course, initially, just like with any scientific advance, everybody said, you're full of it. That's so stupid. How in the world could pieces of the surface of the Earth move around? Well, now we totally believe that that's what's going on. And we have lots of good sound evidence for it. Where do we get that evidence? It starts with seismic waves. So we've talked about them before. This is where they are in the textbook. You have earthquakes, and the earthquakes tell us what's in the earth. When I used that picture before, I didn't realize it was from this textbook. I just found it on the internet. This one here is, hey, look, that very picture was in the textbook. So we have these layers of the earth, the crust, the mantle, the outer core, and the inner core, that we learn about by looking at the waves traveling through the earth. And we have some interesting pictures. I don't think, no, that link's, actually, maybe it is. Come on. It totally gave me an option there. No, okay. Well, I'm not going to take you. This is like a 3-minute video of a child explaining how earthquake waves work. Yeah, it's a child. It's a little cute because it's a child, but it's also useful because it actually is explaining the waves. Well, the waves come in different types. We have, crud. Going to have to use this for my slinky today. So we have different types of waves. The P wave means the pressure wave or the primary wave. And P waves are waves that go like this. I pull this back, let go. It's too fast with this. The slinky is not as fast. But the wave is going the same direction as my spring. So you can see the spring things are just vibrating back and forth this direction, and the wave is also going that direction. That's the key component of a P wave, that you have the wave is traveling the same direction that the motion of the land is. So if you're standing on the ground and a P wave passes underneath, like there's an earthquake on that side of the classroom, it passes to that side, the ground's just going to be going side to side with me. That's what a P wave is. Those waves are faster. The S wave, or secondary wave, is a wave that happens by taking this down and letting it come up, and you can see that it's going up and down in the motion. The wave's traveling this direction, but it's going up and down. So if I had an S wave passing through here, I would go up and down as the wave passes. Fundamental different kinds of motion. And then the last two are more complicated. The Love wave and the Rayleigh wave. The Love wave is also a transverse wave. That is a wave where the ground moves perpendicular to the direction the wave is traveling. But this would be an example where if the wave is going from that side of the classroom to that side, the ground's going to move horizontally perpendicular to that. So that means I'd be going like this as the wave passes that way. So it's a different kind of motion. That's the love wave. And then the Rayleigh wave is a combination of up and down and forward and backward. So that one you roll along as it comes by. So those are your earthquake waves. The top two are what we like to call pure waves. The bottom two are created by combining different types of waves. These waves are, of course, destructive to our homes. How many people again are from California? Wow, that's even more than I thought. So we're at least a quarter Californian in this classroom, which is pretty awesome. And I don't know about you guys because I haven't lived there since you were youngsters, but growing up, we had earthquakes probably on average 1 per year. And they often come in clusters. You guys notice that? So my senior year in college, we had a bunch of earthquakes. The first big one was funny because Paul Kumelang was up in the shower on the 7th floor of the dormitory. The earthquake came, and he was from Maryland. He'd never been in an earthquake. It was his first one. And he thought like the buildings fall down when an earthquake comes. Now, if you live in Haiti, that's true. Because the design of buildings has to be made to withstand what you have here in the United States. In California, our buildings are made to withstand earthquakes so that they will actually sway with the earthquake rather than snap with the earthquake. And things like Loma Linda is currently building a new hospital. You guys know that Loma Linda University is building a new hospital. Their old one is no longer considered safe to be used as a hospital in an earthquake. And so the first thing you have to do is you put in the rollers. Because yes, the hospital is built on rollers. Does that make you feel good? No. It kind of sounds scary. But the idea is if an earthquake comes and the ground moves side to side, the hospital being on rollers will just stay stationary as the ground moves underneath it. Because it has a mass, it has an inertia and an opposition to change in its motion. And so that's why they put it on rollers. And then once again, they make them so they'll flex rather than break. So we build homes that are relatively safe for earthquakes out there in California. So yeah, Paul ran out naked and then he realized, hey, I'm outside. The building didn't fall, but I am butt naked. So then he had to go back in. And we teased him because that's what we do. By the time graduation day, we had an earthquake. After graduation, we all sat down to watch the Laker game. And during the Laker game, there's a big earthquake, and we just all sat there. And after about 3 seconds, one of my friends said, must have been an earthquake. That's what happens when you have a lot of them. So what causes these earthquakes? We have, well, actually, I guess I better stick with the program here instead of jumping ahead. How do these earthquakes help us learn about the earth? By studying the waves, people notice that you have abrupt changes in the velocity of earthquakes. That is, you have an earthquake that occurs, let's say, in Landers, California. And you measure how long it takes for the wave to go from Landers to Riverside and from Landers to Modesto and so on. And you find that with distance, it just increases with time until all of a sudden, whoa, we have a big shift. And so that big shift is because you must have had a big shift in speed somewhere. And so by studying where those shifts in speed occur, they can say, okay, we must have had a change from one type of material to another type of material that caused the change in speed. So in 1906, this dude that I don't know, Richard Oldham, observed that S&P waves, they travel pretty much together until you got to a certain depth. And then they would separate the S wave would travel slower. And what he discovered was the boundary between the core and the mantle, a boundary down deep in the earth. Remember I said that S waves, the shear waves, can't travel through a liquid. And so that caused the separation. 1919, first name I think is Andrea. The last name I know is Mohorovicic. he observed a sharp change at a shallower level. He discovered the crust mantle barrier, the barrier between the crust and the mantle of the Earth. And so we now understand the Earth to have this interesting structure. Now, this here is a region where you have no earthquake waves. Earthquake occurs on the other side of the Earth, you have no waves. Why not? Two reasons. Number one, the S waves can't go through a liquid. Number two, the P waves have such a different speed in the liquid that they go a different direction, leaving you that shadow zone. So in the region here that I marked with blue, there's no earthquake wave that you'd measure. And then the region I'm marking here with red, you measure only P waves, no S waves. The fact you measure P waves means that it went through, it wasn't a vacuum. No S waves means it was a liquid. And then that solid core will have, when the P waves hits it, it will cause waves to come out along the edges. And that's giving you the funky stuff that we see here that tells us about the solid core inside the liquid core. So that's how our information about the interior of the Earth is built. No one's been there. We build it from our understanding of science. So it's kind of useful to know what kind of information they can gather and then how that's being interpreted to get to our understanding. Let's just go because of time. The core is predominantly metallic iron. Why do they believe it's iron? We've talked about this before. There are two reasons. There's one we've talked about before.
Because it's more dense.
Because it's more dense. It's a very common rock in the Earth, and it's more dense, so it should have sunk to the center because it's more dense, what we call differentiation. The second one has to do with the actual speed at which the waves go through it. So there's two lines of reasoning to help them identify it as iron. We don't know for sure it's iron. There is a liquid core of molten iron and a solid core. That liquid core, has liquid iron going around a circle, and that's what makes the Earth's magnetic field as we understand it. How do we know? We use computer modeling of what we understand in physics to say that, yes, if we have that molten core going around in a circle, it'll make a magnetic field like we have for the Earth. How is it that you have a solid core and a liquid core? It has to do with pressure. Extremely hot in there, but the pressure is so high that it actually solidifies in the solid part. So the highest pressure region is solid. Pressure goes down a little, it can be in the liquid form. Temperature goes down a little as you go out, and then it goes back to a kind of mushy solid in the mantle. So here is looking at the Earth as if it was a rectangular thing instead of a sphere. So down the center you have the inner core, the outer core, the lower mantle, which is, well, let's just say mantle and be done with it. The upper mantle, called the asthenosphere, that's the region that's kind of deformable. And so the tectonic plates, the little pieces that Wegener predicted were moving about, float on top of that asthenosphere, and it acts like the grease, if you will, for them to slide. And then on top of that, you have the crust. And the Mohorovicic, otherwise called the Moho because it's kind of hard to say Mohorovicic, is the boundary layer between the crust and the upper mantle. The lithosphere includes a little bit of the upper mantle. Notice the upper mantle goes up to here, and the lithosphere comes down to there. The lithosphere is actually what makes the plates. So it's a little piece of the upper mantle as well as the crust that is sliding about. Now, when you look at this picture, it's real clear. The continental crust is much thicker than the oceanic crust. The reason for that, different kinds of rock. The oceanic crust is largely basalt, which is more dense. Because it's more dense, it sinks down and it forms this thinner layer. The continental crust is more granitic. It's less dense, and it floats up higher because it's less dense. So we have differences, and of course, we're happy to have these differences because we would not survive very well if everything just floated underneath or was underneath the water. We need things floating up high. Okay, I'll stop here. I will pick up with this next time. I've talked about everything on these slides up to here.